Hello, I'm Robert, fact checker and science blogger, and here to help people who are scared of various things, and particularly to help with Facebook to say debunked. And this time I'm looking at this question: does the flap of a butterfly's wings in Brazil set off a tornado in Texas? So, and people get scared about this sort of thing, because I think this lies behind some of the worries of people with OCD and so on, the idea of magical thinking, that doing small things might have big effects. And like people who worry that try and avoid standing on cracks in the pavement because they think it might cause planes to fall out of the sky, that sort of thing. And this might seem to give a scientific background to that, but no, it isn't. This was actually originally set up as a question by Lorenz. Does it? See, it's got a question mark at the end. That is the actual title of his talk. And his answer is no, it doesn't. By the way, if you're wondering about the background, this is water dripping in a cave, and that's a typical example of chaos. And I'm going to bring that into what I'm talking about in a minute or two. So, as you can hear, in fact, the sound is quite irregular, and you can't tell exactly what tip is going to happen. And that's another example. So what he was saying, he didn't say that a particular butterfly's wings can't cause a tornado. Absolutely not. But what he did say is that you have to follow all the flaps of all the wings of all the butterflies, as well as all the movements of everything else. The breathing of animals and of ourselves, and the way we move, the movement of all the trains and cars, the trees, waterfalls, waves, dripping taps, dripping water in caves. And what he actually what he actually found is that all of these, that the weather system is so sensitive to what the conditions are, that unless you knew all the flaps of all the butterflies in the world, then you could not predict when the tornado is going to happen, say a year later. And even with the most perfect computer and most very fastest computer, you still couldn't do it. Even your perfect best models and very fast, far faster than anything we can do, it still wouldn't make any difference. You still couldn't predict it. But it's not just dependent on any particular butterfly. And that's where it's got people confused, thinking that the butterfly flapping its wings maybe sounds a little bit like smoothing air. You think that air is actually getting more and more enlarged and going up into a tornado. It doesn't mean that, not at all. And the butterfly flapping its wings could stop a tornado as well. But actually, what it means, and it doesn't, and the butterfly, no matter how many butterflies you have flapping their wings, they won't increase the number of tornadoes. They won't decrease the number of tornadoes. But what it means is that you can't say when exactly a tornado is going to happen a year from now. And you would have to know the flaps of all the butterfly wings, not just now, but every day, every second, from now on, all the way through to next year. So one butterfly flaps its wings now, but it's also going to matter what the next butterfly does a second from now, and the other butterfly, and 1,000 butterflies another second from now. Every one of those butterfly wing flaps matter, and all the dripping taps. And even if you made it far enough into the future, just random motions of molecules in the air. So eventually it's going to be absolutely impossible to predict, even if you knew all the way down, even down to single molecules. At some point you wouldn't be able to predict that either. So the answer is no. A butterfly's wings flaps can't cause a tornado. And so please don't worry that just doing something will cause something very big to happen somewhere else. It just doesn't work like that. So now we're going to talk a little bit more about this. But so the with a weather forecast, then the errors, to explain a little bit more how it works, that if you have all these numbers, like they go and measure the pressure of the atmosphere in many different places, and then you have the number, and this was how he actually. I wish I could stop those notifications. Anyway, uh, they keep popping up in my videos, and I don't know how to stop them from popping up. Anyway, so if you have a weather forecast, then to explain how this works, it's exponential increase. So the errors, whatever errors you have, they keep doubling in the weather system. So, for instance, we know that the weather forecast for the next day is pretty good. They don't get it exactly right. Sometimes the rain might come at a slightly different time of day or something. But it's usually pretty good nowadays. But whatever errors you have for the next day, every 1.2 days, so roughly every day, if you can think about it, the errors double. So when you get to about a couple of weeks in the future, you're talking about 10,000 times the error for tomorrow. And that is the basic problem with weather forecasting and why they can't forecast the weather in the future for more than a few days and very accurately. And they have made a lot of progress by having probabilistic, and they say 20% probability of rain, 10% probability of rain, 60%. And that's because they're following all the different butterfly flap variations of all the butterflies flapping all their wings and everything else changing all the way through from now till, say, 3 days from now. And they find that some of them you get rain and sometimes you don't. And so they say, well, 20% of all the ones with all the little dripping taps and everything and all the waves on the ocean. And just imagining all of those changing just a little bit on all the ones. So that's why you can't get it even after a couple of weeks. And it's just it's really just a guess, and that's not likely to change anytime soon. And because it's built into the weather forecast, weather itself. Even if you'd have to have a greatly improved detecting of all the motions of everything everywhere, and even then, I'd only just add a little bit to how far ahead you could look. Because you're doubling, another 2 weeks after that is 10,000 times more error again, even if you've got 10,000 times better understanding of what it is like now. So we're not going to be able to predict the weather tornadoes next year, no matter what we do. It's just not. It's just built into the weather. You just can't do it. But what you can do is, and in fact, for a fortnight into the future, although they give these models and you can go look up the weather forecast for a fortnight into the future, at that distance ahead, actually, it's probably more accurate to just go back and look what was the weather on that same day a year ago, or 2 years ago, and the average weather for that day. And that may give you a more accurate weather forecast 2 weeks from now than going by what they do with their weather forecast models. And so the weather is very patterned. And for instance, this time of year on the Albemarle in late autumn, we get lots of storms and lots of rain. And so if you predict it's going to be rainy, it's going to be cloudy, and it's going to be strong winds, then you've got a much better chance of being right now than you would if it was in summer. So that's a strong pattern. And in summer, you'd almost always be wrong. This time of year, it's say cloudy, rainy, and windy. I mean, the windy is a little bit more irregular, but you've got quite a good chance of that as well, especially as it gets further on into the month. So, and then other times of year, it's very dry. And you can just say, oh, there's, for this time of year, you can say, oh, there's a decent chance of a sunny day every, not all certain. So that is the way that you've got all this chaos, but you've also got these patterns, long-range patterns. And that is how we're able to do weather forecasts, do climate forecasts. So that's the whole point in global warming. With the 1.5C global warming, for instance, if it increases half a degree by 2040, they do not mean that any particular year will be, they're not, if we keep on with our CO2 emissions and we don't reduce them, then by 2040 we might already, even before then, we might have our first 1.5 degrees C year. We might have it 2030 or earlier. It's not impossible. But by 2030, I think they say, that would be just a fluctuation, because they only predict the weather over I'm not sure about that. I'll put in, check the description, and I will find out when it is that that is the first kind of year when there's a possibility of 1.5 degrees C actual averaged year. But with the climate forecasts, what they are running with is a 30-year rolling average, because we have these variations which are just like the dripping tap in the I think I'll stop this dripping tap. I can't actually hear it because I switch off my loudspeaker to lack any. I'll just stop it. But you may probably have had enough of it by now. So yes, so a decade. They predict we have these oscillations in the Atlantic and the Pacific that unfold over a quite long period of time, like decades. They're called multi-decadal. And so sometimes the sea is warmer, and sometimes the atmosphere and the heat is exchanged to the atmosphere and the rest of the system. And the warmth is kind of below the surface of the ocean, then it kind of comes up, and then the surface of the ocean then loses it to the atmosphere. And then when the ocean is warmer, then you get the more hurricanes. And then when the ocean is cooler, you get fewer hurricanes, because the warmth of the ocean, it increases the intensity of the hurricanes, because the warm water fuels the hurricane, makes them be stronger. And although it can actually weaken some hurricanes, but that's when you get your really strong hurricanes, when you've got warm water, and that's partly the climate change, and that's partly these oscillations. So the prediction is for the average of the ocean and the land over the whole world, and that average is constantly changing because the heat is moving around and moving deeper into the ocean and up again as well. And so it's just this is a chaos theory thing. It's like a butterfly effect. Some little fish or some butterfly moving its wings could change eventually whether the sea is going to be warmer or colder. But it's not just one particular butterfly, it's all butterflies and all the waves and all the fish and everything. So and all just random movements of stuff. So they just can't predict that either over these periods. So that's why they say that and it's same with the El Nino, La Nina as well. So over long periods of time, then you can, however, it's order patterned with chaos. That's what I called it in one of my articles. I'll give a link if you want to go into techie things. So over the rest of this century, then the average temperature will continue to increase if we continue with our CO2 emissions. It's going to continue a bit anyway, for as long as we do put the CO2 emissions in. But that's going to be an average over 30 years. The average over 30 years is increasing. But over any particular year, so that's, for instance, you have a hiatus when it was more or less steady for about 10 years. That was just this, because of all these fluctuations kind of counteracting, but the underlying warming was still happening. So that means nothing. So if at some point it stops getting warm and it stays steady for a while, that doesn't mean that global warming has stopped. It just means that because they're measuring one particular quantity, they're not measuring the whole system. They measure the average of the sea and the land, and that quantity is not and they could have chosen to track many different things. There was a big discussion back then, what should we use to calibrate and say this is the average temperature, and they chose the average temperature of the sea and the land. They could have chosen the sea, they could have chosen the land, they could have chosen the atmosphere, they could have chosen all sorts of things. They chose the average of the sea and the land, and so that figure will change depending on how the heat flows in the levels of because it's just the surface of the sea, and there's warmth beneath the surface as well. So it just changes how the heat moves around. So so anyway, yes. So I was just going to explain a little bit more about this doubling. So to explain a little bit about why it's so a very simple example, like to understand why, sort of very rough idea, understand how the weather can be so sensitive to such tiny things. And so the way he originally discovered it was that he had a computer program to Lawrence had a computer program to model the weather, and he just set it running. And then he wanted to do the one again, just repeat the previous one that he'd done. So back in those days, he had to type the numbers in again in order to repeat the run. And he typed one number in, but he only did 3 digits instead of 6. Just being late, just saving time, only typing in 3 instead of typing them all in. And he got a completely different prediction. He just ran completely different after a little while. And so that difference, those extra 3 digits, we thought made no difference at all to the weather, made all the difference. And this shows why it would matter. It's easier to understand in binary. I'm going to choose something much simpler than the weather. It's just an operation. You've got to, if your number, imagine this is something you've measured in the real world, like the pressure of the air or something, and it's got a number between 0 and 1. Or say humidity. Humidity goes between 0 and 1, 0 and 100%, 0 and 1 for 100%. So suppose this is the humidity of the air, and you measure it to 12. And I've got to write it in binary. Binary works just like decimal, except you only have 2 digits. You have noughts and ones instead of 0, 1, 2, up to 9. And with decimal, if you multiply by 10, it's the same as shifting it 1. With binary, if you multiply it by 2, it's the same as shifting it all 1 to the left. Like, if you could take 123, multiply 10, it's 1,230. You just add an extra 0 at the end. And with binary, it's the same if you double. And so a 0.11 multiplied by 10 is 1.1, but in this it's 0.11 multiplied by 2 is 1.1. So suppose that was a digit, it was correct to how many decimal places? I think it's 13 places. Then to double it, you shift it to this. Then this operation is what you've got to do is to double it, and then if it's more than 1, subtract 1. So this is not a real weather operation, it's just a very, very simple thing to just show how these sort of things can happen so easily if you've got basic calculations. So just double it, and then you've got to subtract 1, and then you've got those digits. Keep on doing that another 12 times, and you'll run out of digits, and you won't know the right answer unless you have more digits of precision. And that's not very many operations. So it's really quite easy to see why, if you've got a simple operation involved in the calculations to find out what the weather is, like doubling, and then truncating. And that's a very simple operation. You have all sorts of complicated operations in the weather that involve these little details becoming more important. Then eventually, and really quite quickly, you just haven't measured it accurately enough. You just haven't measured your humidity. You should have measured your humidity to 40 decimal places, or to 1,000 decimal places, or to 10,000 decimal places. It doesn't matter how accurately you measured the humidity of the air. Eventually, you just haven't measured it accurately enough to be able to predict what's going to happen. And so, like with weather, then it's got to be 10,000 times more accurate for every fortnight. And so soon, a year ahead, you've got no chance. So that's why it's actually quite simple conceptually once you start looking into it. In a way, it should have been obvious. In a way, if we were a little bit more lateral-minded, then people would have been saying that back in the 19th century. They wouldn't have needed computers. They've just said, that's obvious. But we just don't seem to be quite creative enough to see these things in advance. And nobody even thought of this until they started doing the computer models. I mean, it's actually quite interesting how blinkered we are. How so many mathematicians, thousands of mathematicians for centuries, never thought of this. Until Lawrence did his computer run, and he found that this happened. And yet it's so simple and obvious once you understand it. But nobody even thought of it for thousands of years. or, well, I mean, centuries. We've studied decimals for centuries. And Galileo could have thought of this and written it down, and then someone go and look in an ancient Galileo notebook, and he says, climate is got to be sensitive to the humidity to arbitrarily many decimal places because. I mean, he could have thought of it, but he didn't. So, from quote from his talk. Lest I appear frivolous in even posting the title question, let alone suggesting it might have an affirmative answer. So he's saying no. He's not answering. So that was the question. That's why I'm saying he said no. Does the flap of butterfly's wings in Brazil set off a tornado in Texas? And he answered no. He said less alone suggesting he might have an affirmative answer. He's not suggesting the answer is yes. And so he says, first, if a single butterfly's wing can be instrumental, so also can all the previous and subsequent flaps of its wings. So, every time this butterfly flaps its wings, it's either creating the tornado or stopping it or moving it around. So, and if it can be instrumental in generating a tornado, it can equally well be instrumental in preventing a tornado. But more generally, he's saying that they neither increase nor decrease the frequency of occurrences. Most they do is modify the sequence in which they occur. And the question really is, and then he goes on to say whether two weather systems differ by as little as the immediate influence of a single butterfly. And then he goes on to ask, could there be situations in which a butterfly would flap its wings and there's no effect, because it's kind of isolated from the rest of the atmosphere. And he didn't come up with an answer to that. He said that maybe in calm weather. I don't know if anyone has answered that, but I would think that if you go far, if you have enough time in the future, even the position of every single atom or molecule has to matter eventually. So I think even in calm weather, the butterflies changing position in the atoms and molecules, but even the individual molecules are. It'd be quite interesting to know if anyone knows the answer. I tried a little bit of Google, I couldn't find the answer. But it's quite difficult to actually, I don't think you quite know it from first principles. Maybe you can. If anyone watching this knows, so if I've got any mistakes in these videos, then I'll put them in the description. And if I've got any, and I do this little, if you get a little question mark, a little info, like a little question mark up in the top in my video, then that means that I found a correction, and then you can click on it. And it's actually a YouTube poll, but it means, because that's the only way YouTube lets me annotate the movies now. It used to let you add all sorts of annotations, just add some text along the bottom at any point, but it won't let me do it anymore. So you have to click there, and it says, and then it'll say the little correction, then it'll have a whole series of at least two, possibly several answers, which will give more details. It's a bit eccentric, but it does work, and I can do up to 5 annotations of any mistakes in that way. So if there's any update to this video, then I do that. And then, but you do look at the video description. I'll link it to this video, just a draft at the moment. I'm not sure, but it's going to be a proper debunk. And hopefully it's helped some of you. That no, you don't need to worry about it. The answer is just no. The flap of a butterfly's wing cannot set off a tornado. It doesn't work like that. The popular idea that of the flapping wing, it just seems so intuitive. It's flapping, it causes a little bit of movement. You think of that movement as sort of swirling and getting bigger and bigger and bigger and escalating into tornado, but it doesn't mean that at all. I mean, the amount of any number that you have, like the amount of humidity. If there was a little patch, if your clothes drying, that'll change it. But not just that, just the again, the dripping tap, or like a waterfall. If you have a waterfall, then every single droplet is going to be moving in a different way, and not just as a regular. Every single droplet going down the waterfall is like a dripping tap. It can't be predicted. It's very, very chaotic. So if you've got a waterfall, that's constantly producing lots more confusion into the system than a butterfly flapping its wings. And so it's just a kind of one of these vivid meme kind of things that's kind of spread around because it's quite vivid and looks good, but it's actually not really true. It's a bit misleading. And his answer really is, it's like a question: can a butterfly cause a tornado? And then the answer, which few people who share this meme ever give, the answer really is no. But in the process of trying to answer it, you learn interesting things about the weather.